Alrighty, so before we go ahead and close up the book for chapter 15 and move on, is there any questions that anyone has? Anything you want to recap, review? Okay, cool. So if that's the case, we're going to go ahead and start chapter 16. And Dr. West started chapter 16 on Friday, but he did a lot of like chirality review and then talking about chapters 11 and 12. And I think that kind of freaked people out because he was like, yeah, like you have to go back and relearn everything from 12 and blah, blah, blah. He kind of has a point, but also like don't freak out about it. So what he means is chapters 13, 14, and 15 all kind of went together, right? Because we learned about conjugation, reactions of conjugated systems, then we learned about aromaticity, and then reactions of aromatic compounds. So now we're actually getting back to what we started in chapter 12, which was carbonyls, right? So what reactions of carbonyls did we learn about? Grignards, what did you say? Oxidation reduction, cool. All right, so let's look at page because why would I give myself room? So oxidation reduction. What do you guys remember from oxidation and reduction? Okay, yes. So for oxidation, we're making more bonds to oxygen. For reduction, we're reducing the number of bonds to oxygen. Cool. What did we learn about like leaving groups? You're super general. Yeah, okay. So when we have leaving groups and we have like a reduction reaction, we can react more than one time. Right? You guys are like, no, that's okay. It's a Monday. I get it. So I'm just going to write leaving groups equal R then reaction. Hello, and bless you. And then we also talked about reactivity of carbonyls, right? And that's what Dr. West spent a lot of time talking about. And I just want to recap. We did talk about it sort of, kind of, but I want to go over it like explicitly. So when we're talking about carbonyls, we have aldehydes, ketones, what else? Carboxylic acid, esters, and what's the last one that we kind of learned about? It's like an ester, but with a different heteroatom. Amide, cool. So when we were talking about reductions, we actually split these guys up into two groups, right? You guys remember anything about those two groups? Yes. So these guys were one group, and were they more reactive or less reactive? More reactive. And why was that? There's like two answers. The CH3, what about it? Yeah, it is an electron donating group, but what else? Cool, okay. So when we're talking about reactivity of carbonyls, we're looking for a partial positive and a partial negative. So in all of these reactions, this carbonyl carbon is going to act like a what? Electrophile, cool. So we want the one that has the most delta plus carbonyl carbon because we want it to be a strong electrophile. So that being said, we can talk about those donating groups and stuff now. So between these carbons, right, the CH3s versus this OH or OCH3, which one is going to be more donated? The R group or the heteroatom? The heteroatom, because it donates via what? Resonance. Cool. So all of these guys on the bottom are going to donate via resonance effects, whereas what do these carbons? Inductive effects. Cool. So things that play a role are inductive effects, resonance effects, and one more thing. When you're looking at a CH3 group versus an OH group, what's another big difference there? Sterics, exactly. So the oxygen is huge compared to a CH3. So we're also looking at sterics. So when we want an electrophile, do we want it to be more sterically hindered or less sterically hindered? Less sterically hindered. Cool. So between the aldehyde and the ketone, which one is more reactive? Aldehyde. Cool. And then between a ketone and a carboxylic acid, ketone. Cool. And then ketones and esters and carboxylic acids and amides, we're going to consider those for now to be around the same level. Any questions, comments, or concerns about this so far? Yes. We're going to get a little bit more specific when we go into chapter 17, but now if you have those two distinctions, you should be fine. Yes. So this is just review of chapter 12. I believe. No, we don't. Yes, we do. We're going to talk about this, but we're going to talk about that next time because I want to go over reactions. Actually, we're here. So we said the aldehyde was first. And then number 2 was the ketone. And then we basically said that the other 3 are approximately the same. So I'm going to say, I already named them before, but do you guys want me to write the name underneath? Okay, so I don't remember exactly what he did there, but I think the main point of that is you have the 2 big effects, which are like resonance and induction, and then there. So resonance and induction are basically like charge effects, and like electronic effects. Okay, so we can just do electronics versus steric. And electronic effects is kind of a cheap answer because if you really dive into chemistry, everything can be answered by electronic effects. But what he divided that into is basically steric, resonance, and induction. And we know that resonance is a stronger donating effect because you're actually donating like a whole lone pair. Whereas induction effect basically just has to do with like hyperconjugation and stuff. So you don't really have to know what hyperconjugation is. Just know that it's a very weak donating. Whereas steric, in order to be a good electrophile, you want less hindrance. Fine? Cool. Oh my gosh, how did I not hear that before? You know, I was kind of wondering, like, what are they laughing about? Like, what am I doing? Well, I know the next person that comes in is going to be like, why isn't the volume playing? Because that's what I would do. Anyways, I got completely distracted by that. So I apologize. Okay. So is that kind of helpful? Okay, cool. All right. So now that we've done this, we're going to go back to the first page and we're going to go through all the different reactions. And then we're going to come back to the naming half of this page because that's all like, you don't know any of that stuff yet. Yes. Oh, yeah. This is an amide, carboxylic acid, and while we're here, just so you don't get confused for the next chapter, let's just say amides are number 4. So those are going to be slightly less reactive than esters and carboxylic acids. He didn't really talk about that for this chapter, so don't worry too much about it, but just know that it's slightly more stable. So let's go back. Okay. This is the first time I'm going to say this semester, or maybe I've said it before, I don't remember, but I'm going to say it approximately 8 million times before the end of the semester. So please, at some point, write it down. Okay? An acid catalyst affects a reaction by making the electrophile more electrophilic. So the acid catalyst makes the electrophile more electrophilic. Whereas a base catalyst, I don't know why I wrote making instead of makes, but whatever. So the base catalyst makes the nucleophile or nucleophilic. And while you guys are writing that down, it is written on the top of the SI handout, but I want you guys to take note of this. All of the reactions in this chapter are nucleophilic addition reactions. They all have more specific names, and we're going to talk about each one's specific name, but know that the umbrella term is nucleophilic addition reaction. Okay, so an acid catalyst does what? Yes, so it makes the electrophile more electrophilic, and the base catalyst does what? Perfect. All right. So then we already talked about this, but the carbonyl acts like a what in these kind of reactions? Electrophile. Cool. Ta-da. And then I'll keep this up for a second. Did Dr. West actually start any of these reactions? I don't believe so, but I was on a phone call the last like 2 or 3 minutes, so. No? Okay. Okay, cool. We're gonna start it anyway. But as always, I don't know why when I was making this handout, I was like, that's absolutely enough space. It's really not. So I'm gonna make a new page. But we are going through all of these reactions. We're definitely not going to finish this today. This is going to take at least a couple sessions, and it does feel a little bit overwhelming because they are a lot of reaction mechanisms. Please don't freak out. And if you have any questions at any point, please ask. Yes. So here's the thing. These ones, I recommend knowing them. You don't have to know every single detail of every single step. Like, he's not going to ask you mechanism questions, but a lot of the reagents in this chapter and the next chapter are going to be very similar. So just have a general idea of the reaction and know like the conceptual stuff. So you don't have to know every single arrow, just know the conceptual stuff. And then I'll let you know if there's any like specific things you have to know. Okay. And I'm going to label everything and try to keep it as neat as possible so you guys know what I'm talking about. The first one we're going to do is the Gem-diol reaction. And we also call this the hydrate reaction. And this is when we have a ketone or an aldehyde. And okay, since this is the first one, I won't be lazy. All of the reactions in this chapter are going to have this arrow because it is reversible. Awesome. And also, unless I say otherwise, all of the reactions in this chapter can happen either with an aldehyde or a ketone, and it'll be the same thing. So I'm probably not going to draw out both reactions because you truly don't need that. Just know that either can happen. Yes. Yes. Very good question. And the ketone or aldehyde is always going to be the what? The electrophile. Cool. And specifically, it's going to be this carbon right here that's going to be the electrophile. Okay, so the reagents is something you have to pay attention to in this chapter. The first reagent we have is going to be H2O. And this reaction can happen in acid and in base. So I'm going to show you both actually for this one. And the first one I will show you is acid, because why not? Let's say HCl. And I know I have a habit of explaining while I draw, and I know that can be confusing. So if you need me to slow down or anything at any point, please let me know. Okay, so an acid catalyst affects a reaction by doing what? Bingo! So out of these two, this guy is the electrophile. So the first thing we're going to do is make it more electrophilic. The way we do that is by protonating our carbonyl. So we get, and I'm going to try and keep the color coding. Ta-da. So now that we have a plus charge on our carbonyl, we have an extra delta plus down here because we really, really don't want to have that charge. So now the electrophile is even stronger, it's even more reactive. And in solution, we have H2O still. And we have Cl minus. And I'll draw the. So what do you guys think the next step could possibly be? Okay, great. So what's the idea behind that? Like, why do we think that? Because it what? Perfect. That is a perfect answer. So since it's an addition reaction, we want to have a nucleophile attacking the electrophile. However, the weird thing about this is we know that anything with a negative charge is a what? Base or a nucleophile. Cool. So just like you guys, I would automatically think, okay, Cl minus is a nucleophile. But actually, this H2O is going to be the nucleophile. And so this O attacks here, and we kick up those electrons. This is super similar to what's it called? The Grignard reaction that we saw a couple chapters ago, except instead of adding a carbon group, we're adding an O. The nucleophile. So yes, the reason it's the nucleophile right now is for a couple reasons. So one, it's actually going to be a more nucleophilic atom because O is more electronegative than Cl. And then also, chlorine is a better leaving group than OH is. So if we added chlorine here, it could just leave again. It's less stable. All right, so I'm going to scoot over just a bit. And at this point, what happens to the hybridization of that carbonyl carbon before I draw it out? Yes, so it went from sp2 to sp3 because we added something to it, right? And now instead of a ketone, we have an alcohol. And we got rid of that plus charge now. Yay. And on the other side, we added OH2. So are we happy now? No, why not? Doesn't look good. Okay, what? I purposely left something out. The plus charge, cool. Oxygen has too many bonds here, so it has a plus charge. How could we possibly get rid of that plus charge? Get rid of the H, cool. So I'm gonna scoot over just a tad again. We have Cl minus left in solution. And it's gonna come over here and steal one of these guys. And we get this ugly looking thing. And I'll zoom out at the end so you can see the whole thing. Yes. Exactly. You know, my next question was actually going to be, what do we think this is called? But you already answered it. So, bonus points. Yes. So, like, you mean when this adds, how does it become plus? Okay, so I knew someone was going to ask me this, and I'm glad you did. Formal charge, but I'm going to give you a little, like, cheat sheet right now. So, it's a fun note about oxygen. So, when oxygen has one bond, it has 3 lone pairs, so its charge is -1. When oxygen has 2 bonds, it has 2 lone pairs, charge is 0. And I'm going to scroll this to 10. When it has 3 bonds, and these squiggles just mean it can be to anything, it has only 1 lone pair, and it has a +1 charge. So if you don't remember how to do formal charge, or you're kind of rusty with it, just know this. Yep, we're going to work with oxygen a lot this chapter. We're also going to work with nitrogen. So just know that if nitrogen is a little bit more complicated, but just know that if there are 3 bonds to nitrogen, it's happy. If there's 4 bonds, it's a plus charge. If there's 2 bonds, it's a minus charge. So it's the same trend as oxygen, just it's happy with 3 instead of 2. What was that? Well, we've looked at the charge before. We just never really explained it, I guess. But this was like an Orga 1 thing. Question? Okay, cool. So let me, I forgot what I was, okay, yes. So we're going to call this guy a gem diol. And the reason it's called a gem diol is because there's 2 OHs on the geminal position. What does geminal mean again? Same carbon. Perfect. Yeah, so we're hydrating it. We're adding another H2O. Yes. Great question. So we're actually going to do that right quick because I want you guys to see the difference between acid and base. So I'm going to zoom back in. Ketone again. And we're going to say H2O again. And I'm trying to think of a base that's not OH. That's an acid. Let's say NaI. Sure, why not? All right, so we know that that I has a what charge? Negative. Cool. All right, so a base does what to a reaction? Makes the nucleophile more nucleophilic. Cool. And we know that this guy right here is going to be the nucleophile. So instead of protonating the carbonyl, we're going to deprotonate the nucleophile. So we didn't touch the carbonyl. I'm just going to redraw it. But what we made is NaI. Oh, just kidding. We made HI, which is an acid. And we also now have OH minus. And this is a stronger nucleophile because nucleophiles love having negative charges. Now at this point, what do we think we're going to do? But okay, if we did that, this is a great time to mention this, I guess. So if we took the hydrogen, all we did is move backwards. So in these kind of reactions, there's a lot of places where you think like, oh, we can do this thing. And it's not necessarily wrong. Like you could do that, but the trick is you're moving backwards. So I'm going to mention a couple of those important spots. And this is a pretty good one. So if we went backwards, if we took a hydrogen, we would go backwards. What's the other option? Yes, so I can attack the carbonyl carbon. Bam. And we bring these electrons up. And again, what happened to the hybridization? Yes, sp2 to sp3. Perfect. You do, but we're going to do it in the next step. Okay. So the other thing we have to talk about in these two chapters is chemistry. Chemicals do whatever they want, right? So if I put these things in a reaction mixture, they're going to go book wild. Everything's going to react with everything. It's not going to be like in a nice order like this. So it could, but for the purposes of like correctness in the reaction mechanism, we're going to wait, and you'll see why in the next step. What? For the purposes of this class, exactly. No, literally, because there's like this chapter's not too bad, but when we get to like 17 and 18, people are like, well, why can't you do it in this order? I'm like, you could. I just like this order. It's neat. Or the worst is when I'm like, yeah, it's going to choose to do this. And someone in the back goes, molecules can't choose to do anything. They're not sentient. I'm like, shut up. Like, we made a whole like freaking love story and nobody said anything, but now they can't choose. Yes. Good question. So the reason we can't call it a backside attack is because that carbonyl is flat. So it's going to be like a planar attack. And that's also why we don't really talk about stereochemistry, because it's always going to be like 50-50. Julio. All right. So we're going to draw O. And this O has a charge, and it is what? Negative. Perfect. It has an extra lone pair. And on the other side, we get a happy OH. So at this point, what do? We protonate the oxygen with HI. Cool. So the O is going to go ahead and what? It's the exact same result. Yes, it's just that the steps are a little bit different. And that's why I'm not going to draw acid and base for every single reaction. I just wanted to show you at least for one of them. Honestly, for most of these reactions, he could give you either, or he could even just say catalyst. And there's just a few that like you have to have a specific catalyst. Yep. And it would be almost the exact same thing if you had an aldehyde. The only difference in the product would be H instead of a C. Yes. For which one? Oh, okay. So the product, there's absolutely no difference. The only difference is what charge you get in the intermediate. So if you have an acid, you have a plus charge in the intermediate. If you have a base, you have a negative charge in the intermediate. So let's say there is a little bit more to this reaction. It's not really more to the reaction. It's just like there's different equilibrium stuff we could talk about, but that depends on what Dr. West says in lecture. So I'm not going to tell you anything yet. I'm going to wait till after today's lecture, okay? And then I'll like fill you in on Wednesday. Sound good? All right. So I will zoom out just a tad while I write the next name, just so in case anyone wants to like, I don't know. The next reaction is going to be the acetyl-ketol reaction. This one is not necessarily more complicated. There's just more things you have to remember, unfortunately. So I'll give it one more second and then I'm going to zoom in. So for this one, instead of drawing acid and base, we're going to do one aldehyde and one ketone. Sorry, that was really loud. All right, so I'm going to zoom in. The first one we're going to do is the ketone. And again, it's going to be equilibrium. At some point, I'm going to become lazy and I'm just going to draw a regular arrow. And I will mention that it's at equilibrium. So the ketone in this reaction will react with, where is my green? This. And alcohol. So I drew an R group so that you guys can write that for your notes. And then when I'm actually doing the reaction, I'm going to replace it just with methanol. But a lot of people will get confused and be like, what's that thing coming off the O? Which is valid. And all right, so the catalyst for this reaction actually does matter. So we're going to use an acid catalyst. And at the end, we will talk about why we can't use base. No base. Well, let's just do the acid now, and then I'll give you the little asterisk for base because it's kind of like a special case. All right, so I'm going to delete the R, and we're going to use methanol and HCl. An acid catalyst reacts with an acid catalyst does what to the reaction? More electrophilic. Cool. So this guy is the electrophile, and we're going to go ahead and protonate it. Bam. Bam. So what charge do we get on oxygen now? Positive charge. Perfect. And now we're left with OH, or say the alcohol. We haven't done anything to that yet. And under the arrow, we have Cl minus. That will come in handy later. All right, so this is pretty much the exact same thing we did in the last reaction, so we're just going to skip ahead, or not skip ahead, but move on. So the next thing that's going to happen is our nucleophile attacks and kicks up these electrons. And while you guys are drawing that, I want to take this time to say that whole thing is the nucleophile, right? But specifically, this oxygen is the nucleophile. And that's very, 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 oh, too many varies. It's very important that you know what atom specifically is a nucleophile, because people get mixed up in how to connect this all the time. So I want you guys to be very careful. Yes. So the heteroatom is the nucleophile, and specifically, this carbon right here is the electrophile. I saw a hand somewhere. Yes. Exactly. So this whole molecule is a heteroatom, right? That whole molecule is the nucleophile. But you have to know that the oxygen is the thing that's specifically doing the attacking. And that carbon that I highlighted is the specific carbon that's getting attacked. And the reason that's important is when we draw out the next step, this O is single bonded and it has an H on it now, and it's all happy and no charge. This oxygen from the alcohol is attaching to this carbon, and then whatever is on the nucleophile is attached to that heteroatom. So oxygen goes first, and then here we have one CH3 and one H. So just to repeat, the heteroatom is going to directly attach to the carbon, and then whatever else is on the heteroatom comes after. A lot of students will attach the carbon here because that looks similar to the Grignard reaction. Do not do that, please. Question? Or just? Yep. Okay. So now, at this point, what are we thinking? Just in general, what do we think about this? Yeah. Yes, we are missing a plus charge right here. Awesome. So how could we possibly get rid of a plus charge? We could definitely deprotonate. Cool. So, okay. We have Cl minus. Bam. Bam. So now we have one side is an OH. The other side is an OR. Now the charges are all balanced out. Do we think we're done? The little laugh that people did were like, ah, well, I did, but now you said that. No. Okay, so we're not, unfortunately. The way we know that we're not done is, unlike the gem diol where there were two OHs, those two OHs are exactly the same. This one has one OH and one OR. Those two groups are different. Before I tell you what happens next, I am going to write down that this is a hemiketal. Half a ketal. Yeah. And I'll show you what a ketal is. But a hemiketal is one OH and one OR. So, the reasoning behind why we're going to continue this reaction is because this was sp2, now it's sp3, and sp2 is more stable than sp3 is. So we want to go back to sp2. And unlike the gemdiol, where getting rid of one of these would pretty much be going backwards instead of forwards, here, if we get rid of this, we go forward and get a new product. So let's try doing that. Okay, what do we have left in solution? I'll ask you guys that. HCl. Cool, so HCl. So how does an acid catalyst make a reaction better? What? More electrophilic. This is an ugly arrow, I apologize. Ta-da! So we are going to protonate the OH this time. And why do you think we're protonating the OH? So it could be a better leaving group. Perfect. So I'm going to duplicate this guy because I don't want to reach a row. And now what's the charge if we add a hydrogen? Plus. Cool. Oh, you can't see that. All right. So let's throw another arrow. What do we need to do in order to kick off that leaving group? Think back to Grignards and reductions. Everyone's like, that was 2 exams ago, man. Yes. How could we make that, like, how could we make the leaving group leave? Nope. Good thought, but nope. We're going to do that eventually, but we don't have a carbonyl. That's the one. Okay. So if we use these electrons to form a double bond, remember, the reason we're making that a leaving group is to get sp2 back, right? So we're going to reform a double bond, kick off the leaving group. So we get bam. How do we feel about this guy? Everyone's like, I don't want to answer. Yes. So it is sterically hindered, but the biggest reason is that we wanted to form sp2 again. So if we were okay with sp3, we would have just stopped at the hemi. Yes. So for all of the reactions, it's going to prefer sp2. But for example, the one we did before this, the reason we stayed sp3 is because these two groups are exactly the same. So if we try to make one of them leave to form sp2, we're not making a new product, we're actually going backwards. If we were to reform sp2, yeah. Yes and no. Yes, because it's the only one that's different, but no, because it could reform it, but that's just going backwards. So that's why it's reversible. It is going to reform, but it's going to go back to this form instead of making a whole different thing. It is at the end, but remember, these are reversible arrows. So it's not saying that it's always going back to this one. It means that it's going back and forth all the time. Yes. Perfect. Someone pointed it out. So what's wrong with that? Why don't we like it? Why'd you point it out? There's always something, yes. What's wrong with it? It has a plus charge. Ugly. Yes. Absolute garbage. All right, so how do we get rid of a plus charge usually? You deprotonate it. Cool. Can we deprotonate here? No, why not? It doesn't have a hydrogen. Perfect. Okay. So what do you do if there's a plus charge and you don't have a hydrogen state? We could, but if we do resonance, all we do is put a charge here instead, right? That's a good idea. The only issue with that is you can't really move from an O to a carbon. Like methyl shift would just have to be between methyl. Evelyn, do you have an idea? You said it earlier. Did. Yeah, okay, so in English, no, I'm kidding. But what we're gonna do is we're gonna get another molecule of our alcohol and we're gonna attack again. Because why not, right? So I'm gonna give you a different color. We're gonna get even better. Look at the ugly products we get, okay? So what's gonna happen is, again, in solution, we have Cl minus. Cool. All right. This O is gonna attack, gonna kick up these electrons. And yes, we could have deprotonated first, but I didn't want to. So now, again, we go from sp2 to sp3, which is what we were trying to avoid in the first place, but whatevs. And now we have, again, the O is the nucleophile, so we attach the O to the carbon. Are we happy? No. Because, can you even be happy in orgo? Debatable. So we have Cl minus this time. That can just go ahead and deprotonate. Yay. And I am going to draw the final product just because we are technically late. I know. Time flies when you're having fun. Everyone was like, shut up. That's not fun. Alrighty, so 10 years later, we get our acetal. Just kidding, our ketol. And this is one of the reactions where I'm like, absolutely do not draw out this whole reaction on your exam. Do not do that, because it would take so long, and also by the end of this, I would be crying. Like, I'd be like, there's no point, I'm just gonna drop out. All I want you to do is, okay, we have a ketone, we have an OH, and we have an acid, right? We're gonna put 2 moles of this on our carbonyl carbon, and we get a ketol. And I want you to know that this is our intermediate. And so the little note, we're going to talk about this more next time. If we had a base or no catalyst, we stop at the hemi. So if we had a base catalyst or we had no catalyst, we stop right here. We do not go any further. Yes, I agree. Yes. Absolutely not. I wanted to show you the full reaction today. Starting next time, we're going to go through all the simplified reactions. Because I personally don't want to draw this out every time. Nope.
50 minutes.
Nope.
Questions like this.
No. We have the Rosemary method for all of these reactions, which is a total of 2 steps. So, yeah, that's the hope. Have fun in class.